Hello everybody and welcome. I am continuing my discussion of the human mimicking robot hand on the topic of how, or showing how it will have the strength that I want it to have. I do have a YouTube channel named Patrick Gray and I invite you to subscribe. I think you'll like it. I have a website, Piston Robot. You can go to the menu, you can go to discussions about a robot. There's a page here, Give the Robot a Hand. That's where I discuss this. I do have there an FBX export where you can open the robot hand in your own 3D drawing program. I do try to always remind everyone any real object might hurt somebody. If you have a real object and you are managing it, you should manage it in a way that is legally allowed and reasonable and safe. And if you can't manage that object in that way, then my advice is don't create it as a physically real object. I have already discussed the criteria I think that a proper robot hand should have. I do think a lot of people are going to say, yeah, well, that's not really possible. I think it is possible. I have some introductory remarks that I did in part 1 about the strength of the hand. This is part 2, so I'm not going to do all that introductory stuff again. Here is the YouTube for part 1 if you want to see that. And this is the link for it. And the name of this YouTube is Give the Robot a Hand Strength Discussion Part 1. And this video that you're watching now is Give the Robot a Hand Strength Discussion Part 2. Alright, and we're in SketchUp. Here is the robot hand holding on to a metal bar. It's green, but it's metal. And this is going to hold up 200 pounds. In order for this to work, these fingers have to be curled over and they have to stay this way. Even though the hand is pulling that way with 200 pounds, or the bar is pushing that way with 200 pounds, the fingers have to stay curled over. And the way they stay curled over, and we're using the same anatomical convention that human beings have, which is these very strong ligaments, they go back into the forearm to very strong hydraulic cylinders that pull on them. I have another lecture I'll do about figuring this out, but they need to pull with 113 pounds of force in order for this finger to support 50 pounds. And we want to hold up a 200-pound robot. We got 4 fingers, so that's 50 pounds per finger. The thumb is there, but in human beings, the thumb doesn't, it helps to stabilize it, but it doesn't really add any pulling power. And you can see when the hand is curled over into the thumbs up sort of position, all right, that this final phalange here can be pulled over that way by this ligament. And we're doing a strength discussion, and I was looking specifically at this place where this phalange runs into this corner. And that's really what I was looking at. The original design was this distal phalange would just rotate around this bolt and it would be pulled by the attachment of this strong ligament flexion. This is the ligament that causes flexion. It's connected to the distal part of this distal phalange. And what I realized was if you just simply take that phalange and start pulling on it, the phalange itself will run into the proximal end of the distal phalange, will run into the distal end of the middle phalange, and it will hit right here at this corner. It's rotating around this bolt. And if you do measurements, this is the axis of rotation. So this distance here, which comes to 0.15 inches, and the connection point is down there, and so that distance comes to 0.81 inches. And so if we look at that ratio, 0.81, the long one, divided by 0.15, the short one, that comes to 5, a ratio of 5. So it's a 5-to-1 increase of force. So if you're pulling on this with 113 pounds of force, then the force that you're going to be creating right here is 5 times that, which is 560 pounds of force. And 560 pounds of force, if you look at this bolt, this is the cross-sectional area of the bolt, 0.0024 square inches times 65,000 pounds per square inch, which is the yield strength of the alloy 2205 stainless steel. This bolt has a shear strength, well, has a tensile strength of 156 pounds. The shear strength is about half of that, which is 75 pounds. Now there's 2 places where it interacts, so it really, for a 2 connection place, it's 156 pounds, but 156 pounds is less than the 550 pounds. And so I realized that this design needs to be changed, and what I created was a connection between the middle phalange and the distal phalange that has this double bolt system, and it has this stop or end point for that distal phalange to come down to. So the distal phalange is here, and it's being pulled by this strong flexor ligament with 113 pounds of force, and this distal phalange runs into this stop, and this distance where it runs into it is about halfway. So what that means is, if this has 113 pounds of force going that way, then this has 113 pounds of force going that way, and this bolt can tolerate that. And the reason I doubled these up is because since it's a 2-to-1 ratio here, if this is pulling with 113 pounds of force, then it's going to be pushing on this green stop block with 226 pounds of force, which is beyond the 156 that the bolt can tolerate. And if you put 2, it's 300. But 226 pounds is pretty close to 300, and the easiest way to fix this problem is to just convert these bolts. These are M1.4, so they're 1.4 millimeter diameter alloy 2205 alloy stainless steel. They can be converted to M1.4 titanium bolts, and titanium, the T6 titanium has a yield strength. The T6 alloy titanium, which is the one that everybody uses, has a yield strength of 145,000 pounds per square inch, which is basically twice what the 2205 alloy stainless steel has. So this bolt will have a shear strength of 300 pounds. It will have a tensile strength of 300 pounds, but it will have a shear strength of 150 pounds. And it's touching at 2 places. So that brings back up the shear that can be placed on this bolt from 150 to 300, and there's 2 of them. So that's 600 pounds. So you have 226 pounds of force pushing against an anchor point that can take 600 pounds of force. And so what happens is you have now, with this structure, created a joint, an end joint for the middle phalangeal, distal phalangeal. This joint is called the distal interphalangeal joint. You have created a structure that can withstand the forces that are on it. And you'll notice that I also beveled this proximal phalange. I beveled it so that you have a nice flat surface to take the pressure of this. And it is, you'll see up here in these are originals from the other form. I put the double bolt part in here, but this corner here, that should have been taken off, and that allows this phalange to rotate down. Although surprisingly, this is part of why I wasn't quite sure about this, was that I think when this rolls over like this stuff, these different parts are going to start running into each other. It may be that this, in the curl up position, this phalange is not going to actually have that lever action problem. But I wanted to have it where we don't have to worry about it. It's the same sort of situation here where I'm not sure in a real situation holding this iron rod if that phalange could be pulled down into an interaction here. But it's not that hard to do, and that way you don't ever have to worry about it. And it means that the pulling force of this strong flexor ligament is not going to be able to damage this distal interphalangeal joint. And all the rest of the joints, I have one where the hand is straightened out, but you'll notice that in all the rest of the joints, the interphalangeal articulations do not include angulations where the one phalange is going to run into the other one. So this double joint with the rest stop probably needs to be present at this distal phalange. And thought I would show you, this is 4 versions of the hand. In the human hand, the fingers do not extend beyond this 180 degree. So we don't have to worry about this going up that way because human hands don't do that. The thumb, again, it has this double bolted stop because the final distal phalange of the thumb can be pulled down to cause that problem. But in all the rest of these poses, this is the thumbs up position where the fingers are kind of twisted around as much as they can be. You'll notice that these other joints are not, they don't have that problem of the phalange, of one phalange bumping into the other one. And this is sort of one where the metacarpal phalangeal joint is straight, and then the interphalangeal joint and the distal interphalangeal joint, this is the proximal interphalangeal joint, this is the distal interphalangeal joint, but this one is not turned enough for this to run into anything, and this one has that safety feature on it. And again, we have where it's grasping the metal bar, same deal in the proximal phalange to middle phalange. The angulation is not enough where anything is running into anything. So all those problems don't exist other than this one potential place. And again, it's also present in the thumb because the thumb really could curl down this distal phalange, but we've got the protector in there to stop that. And again, now she's given me the secret message that the clock is ticking. I'm going to show you in the next video how we can establish whether these metal parts of this pulling yoke are generating forces beyond what they can tolerate, and the same is true for these bushings, but that would be the next YouTube video.